Hello, everybody. I want to walk you through the example from the script that I call friends. So we have two friends, A and B. A likes action movies, B likes comedy, and we put scores on them. So that we get a diagram of preferences for A. Action, comedy, and for B, we have a 2x2 table, and A likes the action. If they go together, he is not totally opposed to comedy, so he gives it a score of 1. But if they're not together, he gives it a score of 0. With B, it's the reverse. It's action, it's a score of 1. Comedy gets a score of 2. And also, when they're not together, B gives that a score of 0. They still prefer the companionship. If that's not together, then it's not worth going to the movies at all. So we got two 2x2 tables, and we can combine these two tables into one. Action, comedy, action, comedy. If you just put pairs of numbers, 2, 1, 1, 2 in the lower right corner, and then we have 0, 0, and 0, 0 for the two situations when they are not together. When friend A chooses comedy and B chooses action, so that would be the top right. And when friend A chooses comedy but B chooses action, that would be the lower left, and that gets a score of 0 from both. The next step is that both friends assign probabilities to these choices. So, of course, they've got to make a decision, one or the other, but think of the same situation repeated multiple times, and they just go in 1/3 of all cases to that, 2/3 of all cases to the other. So we can imagine that it sort of makes sense to assign a probability to each of their choices. But because there's only two choices, the probabilities have to add up to 1. If we call the probability for A's first choice P, then A's second choice will have probability 1 minus P. Call the probability for B's first choice Q, then B's second choice has to have probability 1 minus Q. This is already in the script as a diagram. Now we can calculate expected values for A and for B. Expected value for A, that just means we use the first number from each pair, so it's the numbers from A's table. For all 4 situations, and we need to multiply each outcome, each score, by the appropriate probability. So the probability of action and action, they both choose action, is simply P times Q. by the multiplication rule. The probability of A chooses action, B chooses comedy, that would be the lower left situation for which they have a score of 0, but it doesn't matter. The probability for that is P times 1 minus Q. Other way around, comedy for A, action for B, that choice gets the probability 1 minus P times Q. And finally, comedy, both go to the comedy movie, gets the probability 1 minus P times 1 minus Q. That is the 4 probabilities that we need to calculate this expected value, which is the score 2 multiplied by the probability P times Q. Then the score for action comedy is a 0. Score for comedy action and action comedy, both zeros. We don't need to even write that. We can skip straight ahead to the last one. That's a score of 1 times the probability 1 minus P times 1 minus Q. All right? But since we want to do things with this expected value, we want to make it as big as possible if we are A. We want to get a grip on that. We want to rewrite it. And the first step is to expand it. You may also have seen this in high school, maybe as FOIL it out. Just copy the 2PQ. And what do we have here? We have a 1 minus P, and then a minus Q, and a plus PQ. We get 4 terms. Then we gather up everything with a P in it and factor out the P. So what is that? It's a 2Q minus 1 times P. This takes care of that one and that one. What is left? Oh, shoot, I'm sorry. I've got the last PQ in the corner there. That's, of course, another PQ. So let's just change that and turn this 2 into a 3. Which, of course, means this 2 becomes a 3. Everything's good. What is left over? What do we still need to take care of? This is a plus of 1 minus Q. And now we really have taken care of the entire formula. This is the expected value of A expressed in a more useful way, because now we can determine what choice of P will make this as big as possible. But the choice depends on Q. Usually, it depends on Q. The first thing that should spring to mind is, what if 3Q minus 1 is 0? Then this P here gets multiplied by 0, so it doesn't matter what A chooses. This happens when Q is 1/3, and then A's choice of P, that's A's decision, does not matter. Curious, but that's what it is. Next possibility, 3q minus 1 is greater than 0. We're always focusing on this parenthesis, 3q minus 1. Then, well, to make their expected value as big as possible, A will want to choose P as 1. And to rewrite that inequality, it happens when Q is greater than 1/3. And the last one, if 3q minus 1 is less than 0, then A wants to choose P is 0, because the P in their expected value gets multiplied by a negative number, and that means A just wants to limit the damage, minimize the damage here, so make that P as small as possible, and you can't have negative probabilities, so the smallest value you can choose is 0. They will do that, choose P as 0, and this is all happening when Q is less than 1/3. Now we've covered every possibility. We've got a rule for A how to best choose their P, except it doesn't matter what they choose in the special case when Q is 1/3. So far, so good. Next thing, we can do the same thing with B. And there we get similar rules. 1 times PQ plus 2 times 1 minus P times 1 minus Q. I'm looking at the table for B, which I wrote separately over here. And I used to give B the color blue and A the color red. Go back on that one. Give A the color red. So we're looking at the table for B and using those numbers to calculate the expected value for B with the same probabilities. Expand it out. And this time you get 3PQ minus 2P minus 2Q plus 1. This time we want to have a decision rule for Q, so we gather up everything with a Q in it and factor out the Q. So what's left? It's a 3P minus 2 times Q minus 2P plus 1. And the choice of Q doesn't matter when 3P minus 1 is 0. 3P minus 2 is 0. Choice of Q, that's B's decision. B's choice does not matter. For their own expected value. And if 3P minus 2 is greater than 0, same kind of deal is happening, then B wants Q is 1. If 3P minus 2 is less than 0, then B wants Q is 0. And those two things happen. The first one happens when P is greater than 2/3. And the second thing happens when P is less than 2/3. And the top is when P is exactly equal to 2/3. So that's a set of 2 times 3 different rules or cases. And it's really much nicer to put all of this stuff into one diagram because it's easy to see what's going on then. So I drew this unit square. Where you can put every possible choice for P and Q. So the horizontal axis is the P axis, vertical axis, the Q axis. Here's the origin. And we had as the first decision rule way up front, first thing we considered, Q is 1/3. Then A's choice doesn't matter. Q is 1/3. That's a horizontal line. And it is about here. Whenever we are in a situation with the choice of P and Q that is on this line, the choice of A doesn't matter. When Q is bigger than 1/3, then A wants to choose P as 1. So I put an arrow. Red arrow because it's A's choice. A chooses P is 1. So we will end up on the right side of the unit square. That's where P is 1. So wherever you are in the top half of your unit square, A wants to go to the right side here. When Q is lower, then A wants P is 0. That's the left side of your unit square. And the arrows tell what A wants, depending on B's choice. And then we can do the same thing for B. I mean, we have the rules, we worked them out. So when P is 2/3, B's choice doesn't matter. P is 2/3. That is a vertical line, which is about here. And we just worked this out. P is 2/3, then the choice of Q doesn't matter. If P is greater than 2/3, that's on the right, in the right part of the unit square, then B wants Q is 1. So we make an arrow going up to the top. I want a blue arrow. That's what B wants, going up to the top. And if we are on the left side, then B wants Q is 0. So we make an arrow going down. All right. This diagram with these arrows tells us everything what's going on about equilibria. First, whenever we are anywhere in the top half of the square, say, in the top right corner, so say here, then A says, I want to go over here. And B says, I want to go there. And if you then look at the other friend again, A says at every point, I want to go to the right. So if they take turns reacting to each other's decisions, no matter where they are in the top right corner, they will end up exactly at the top right corner of the square, right here. That's why this point is a stable equilibrium. You got arrows, blue and red, both pointing towards it. The point 1, 1 is a stable equilibrium because arrows, blue and red, point towards it. The arrows in the neighborhood. The arrows that are close by. There's arrows that are far away, which point away from it, but that doesn't matter. Close by, the arrows point towards it. So both friends are happiest there than at any point in the neighborhood. If anybody changes their decision by accident, just by a little bit, they will come right back to this decision 1, 1, where they both choose the action movie. So far, so good. The same thing happens at the point 0, 0. Another stable equilibrium. Oh, I didn't finish the writing because arrows in the neighborhood point towards it. This point is another one. And now the last one, this deal always happens when the two lines where the decisions do not matter intersect. There we have an unstable equilibrium. So this is the point 2/3, 1/3. This is an unstable For one thing, each friend could modify their choice, change it by a little bit, even a lot, and nothing changes for them. So they don't improve their expected value. By changing their choice. But the key is the other friend does not change anything. The other player or friend keeps their choice the same. Now, if red changes a little bit, you travel along the red line, and that doesn't change for red. If blue changes a little bit, nothing changes for blue. But if both of them change at the same time, even just a teensy amount, you could travel diagonally towards the top right, and then they would both say, hey, we're not good here. We want to go somewhere else. And so they drift away from that equilibrium and end up in the top right corner. If they drift diagonally a teensy bit to the lower left, either that way or that way, again, they will drift away from that point at unstable equilibrium and end up in just 2 moves, zap, zap, at the point 0,0. So it's a situation similar to when you balance a ball on your nose, even a teensy bit to the left or to the right, and the ball will fall off. And so that's an unstable equilibrium. Okay, so that's the friend example. And I'm thinking the other examples work exactly the same, with one exception, that probabilities sometimes, this comes into play, that probabilities have to be between 0 and 1. And sometimes you can get things like an expected value where you have 2p plus 3 times q plus something else. So in that situation, 2p plus 3 could never be 0, because you can't have a negative value for p. Similarly, you could have 3p minus 6 times q, and that will always be negative. Write that equal sign nicer. And that's because p cannot be 2. It always has to be less than 1. So that last thing actually happened in the prisoner's dilemma. But the computations are very much the same. Those PQ and so on probabilities happen in every single one of these examples. So I'm thinking you're best served by going through this example very carefully and then see where it leads you with the numbers from the other examples. Interesting last point is to look at the possible ways the arrows can go. And I might make a separate video about that. This is long enough, so I'll stop here. Hope you get something out of this. Thank you. Goodbye.